All right, so in this video, we're going to talk about the integration technique of partial fraction decomposition. And what I have out here front is really just where you have a polynomial over a polynomial. And the process, the partial fraction decomposition, is going to come into play when q of x, the denominator, is factored completely, absolutely completely, almost feels like it's over-factored. And so much of what we discuss in this video is going to be purely algebraic. The whole idea of partial fraction decomposition might be new to most people, even though it is algebraic. So let's talk about that before we get into using it for certain integrals. Okay, so let's take a look at the example I have up here as well. Say consider this rational expression. So in order to combine these two terms, we of course would need an LCD. And so the LCD being x minus 1, x plus 2, means that I'm going to need to multiply this first one by x plus 2 over x plus 2, and this one by x minus 1 over x minus 1. In doing this, we'd get a 2 times x plus 2 minus the quantity x minus 1 all over the x plus 2 times x minus 1. And if we clean this up just a little bit, we would end up with x plus 5 over x plus 2 times x minus 1. Now, that might have been the easiest problem we've worked in a while, but what we're going to be doing, and the purpose why I went through this with you, is we're going to be decomposing, meaning we're going to be taking stuff like this, and we're actually going to be working backwards into stuff like that. Okay, so we'll be given these types of things, and it's going to be our job to construct this, to decompose this into this. If you think about it in terms of an integral, which we're not going to work this one entirely, but if I ask you to integrate that, and I ask you to integrate those, clearly this one's a lot easier, right? And that's our goal. And so let's take a look at a few examples. Okay, so you can see this first example here. There is no integral. This is, again, nothing but algebra at this point. And I did mention on the last screen that we had to make sure our denominator was factored completely. So for this one, we would have an x and an x minus 2 and an x plus 2. All right, since we have now three factors, 1, 2, and 3, I'm going to have now three different terms that I'm going to add together. In the denominators of each of these, I'll have an x minus 2, and an x plus 2. The order doesn't matter because, remember, it's addition, but I want you to think ahead now a little bit why we're doing this. If I were to take all three of these, even not knowing what the numerators are, and I were to condense it down into one, my LCD would be x minus 2, and x plus 2, as I have here. Okay? Now, for the numerators, let's come back over and look at each of these individually. Now, when we see something like an x, that is a linear factor, okay, an x to the first. So that's going to be linear, that's going to be linear as well. So all of these are linear. Now, for these things to be proper fractions, we need something smaller on top than on bottom. Well, the only thing smaller than a linear function would be a constant. So I'm just going to go ahead and put an a on top. Same thing here, I'll put a b and I'll put a c. All of these a, b's, and c's are constants because they have to be less than the function in the denominator. Okay? So now, from here, we could go ahead and we can combine all of these things again. Now, remember, we're decomposing, so that's ultimately what we're going to do, but we still would need to figure out what a, b, and c are. So I would carry it on a step further to where I would have this a times x minus 2 times x plus 2 plus a b times an x and an x plus 2 plus a c and an x minus 2. And that's all over the x minus 2, and x plus 2. Okay, so again, to combine these into this, I just used my LCD, and as we have in the past, and we came up with this. But now what we've established is that this numerator has to equal this numerator right here. Okay, so that's going to give us a 5 equals the a x minus 2, x plus 2, plus bx times x plus 2, plus cx times x minus 2. So this right here is what's going to allow us now to solve for the A, the B, and the C. Now we're not going to do it in this example. For now, I just really wanted you to get this set up. But this right here would give us a system of equations, in which case we could then solve for A, B, and C. Once we know what A, B, and C are, we'd go back and plug them in here, here, and here. And if this were an integral, you can see how simple these integrals would be compared to what we would have started with at the beginning. Okay, so for this one, we're going to do the same thing. We're just going to decompose this into however many terms, and then whatever we have in our numerator, we can then set up a system if necessary. All right, so once again, the denominator has to be factored completely, and this is almost obnoxiously complete, where we would have an x plus 2, an x plus 2, an x plus 2, and an x plus 2. I'm a big fan of doing this because now it's going to remind me that I'm going to have 4 things that I'm going to need to add up, since I have 4 factors down there. Now, pay close attention. I can't just put an x plus 2, an x plus 2, an x plus 2, and an x plus 2. Okay? I can't do that because when I combine all of this, my LCD would just be x plus 2. So instead, what we're going to have to do is use all possible combinations. So I'll put a squared on that one, I'll put a cubed on that one, and I'll put a fourth on that one. Okay? Now, again, if that's not quite making sense, think about it going backwards. If I gave you all of these and I said, find me the LCD, well, your LCD would, of course, be the x plus 2 to the fourth, but these being less would also be included in that. And so remember, we have to exhaust all possibilities, because while this might be too much, it might not be. And this is the only way that we can get all the necessary information. Okay, so again, circling back now to the individual factors, once again, it looks like all of these are linear. So the only thing smaller than linear would be a constant. Therefore, we would have constant A, constant B, constant C, constant D. Okay, and so remember, when it comes to these repeated factors, you have to exhaust all options, and then when it comes to noting what goes on top, it always comes back to the original factored form. These were all linear, and therefore constants A, B, C, and D. Okay, so for this one, we actually are factored completely in the denominator, so that means there's going to only be 2 terms now that we have to work with. We would have this x minus 1 and this x squared plus 6. Okay? Now, from back to the original, that's linear, but that's quadratic. And so on top of the linear, we would still want just the constant, but on top of the quadratic, we need something smaller. The thing that's smaller than a quadratic would be a linear function, so maybe a bx plus c. Now, I know that a constant is also less than a quadratic, which would still be a proper function, but remember, we have to include all possible options. If this truly should just be a constant and not a linear function, then when we solved our system, we would just find out b was 0, and we would have only a c. But we have to make sure everything is accounted for so that we don't overlook something in the process. All right, so the last example we'll look at before transitioning into some calculus is this one up here. And much like the others, I would want to go ahead and factor that denominator completely. So that would be an x squared plus 1 and an x squared plus 1. So we would have 3 terms, since we have 3 factors. And we would have our x minus 2. And remember, that's going to be an x squared plus 1. And then we would need that x squared plus 1 to the second as a possible option then to give us the same least common denominator that we started with. Okay? Now again, coming back over to these, you can see here linear, quadratic, quadratic. So the thing less than linear would be a constant a. The thing less than a quadratic would be the line, bx plus c. And then we would have another one for this factor here. So that would be a dx plus e moving down the alphabet. So there's our expansion, our decomposition. As I pointed out to you in our first example, we would then carry it a step further and put it all back together. So this would be a times x squared plus 1 squared plus bx plus c times x minus 2 and x squared plus 1, and then plus dx plus e times x minus 2. And this would all be over our LCD of x minus 2, x squared plus 1 squared, at which point then we could take this numerator and this numerator, set these two things equal to one another, then allowing us to find a, b, and c, d, and e by solving a system. And that's what we'll do once we get into the applications here in just a little bit.